Greetings, math people. So we have another episode of Mr. Arrington versus the textbook. We're actually tackling the same topic as we did in the part one video. So in the part one video, got a little feedback, people trying to challenge my position. And so I'm going to state it more in this particular video, a little more emphatic with a little more evidence. So the whole thing is, in essence, the base example is the claim. I claim that the function f of x equals x cubed is strictly increasing is false. And my claim is that the function is increasing from negative infinity to zero and from zero to infinity, but not at zero. And I understand that this is not the prevailing view or the most popular view. I'm fully aware of that, but I still believe it's the most correct view. So in the first video, I've looked at the particular claim that that x cubed is strictly increasing in the pre-cal book. Today, I'm going to look at it in one of my favorite calculus books, Calculus by Larson. And in this book, they try to look at this debate, if you will, in a little more detail to try to prove the point, their point, that is that the function is strictly increasing, the function being x cubed. So let's look at how Larson presented their case. So they presented a very good case, by the way. So they're very well of this debate. And what they have here is the graph of x cubed, and they show it. They demonstrate that it's increasing. And what they're trying to juxtapose is the point where you think this function is not increasing, as they show that type of example is shown here. And so here is some piecewise function. And the piecewise function, the function equals negative x squared when x is less than 0, 0 when x is between 0 and 1, and x minus 1 squared when x is greater than 1. And they're showing here in this particular example that the function is increasing, constant, and increasing, but not so here. And if you read the little paragraph here, it states a function is strictly monotonic on an interval when it is either increasing on the entire interval or decreasing on the entire interval. For instance, the function f of x equals x cubed is strictly monotonic on the entire real number line because it is increasing on the entire real number line, as shown in figure 3.17a. There's the figure there. The function shown in 3.17b is not strictly monotonic on the entire number line because it is constant on the interval from 0 to 1. Great case, Larson. Great case. But I'm going to prove you wrong as well. Now, a key component in this argument that x cubed is strictly increasing is the position that a function can only increase or decrease on an interval, not at a point. So the position is functions don't increase or decrease at points. They increase and decrease at intervals, meaning the only way you can tell if a function is increasing, it must be from some comparison from one point to another. As you go from one point to another, did the function increase or did the function decrease? That's the only way you can tell if a function is increasing, the prevailing view states. Okay, interesting. Quite interesting. Let me move this book out of the way, if I will. I love this book. It's a great contribution to society, right? But let's move it out of the way for a second, and let's dissect this function for a minute, if we may. So the function is f of x equals x cubed, and the graph looks something like this. And the claim is made that you can't determine whether a function is increasing or decreasing at a particular point. that must be confirmed on an interval. Okay, cool. So let's say I take the derivative of this function. That derivative is 3x squared. And if I set that derivative equal to 0, I get x is 0. It's a point where the derivative is equal to 0, which is called a critical point and also called a stationary point. Now, understand the claim. The claim is that a function cannot increase, and I'm stating the claim of my opponents, is that a function cannot increase or decrease at a point, right? That's the big part of their position. And I claim that this function at x equals 0 has what is called a stationary point. What is a stationary point, you may ask? Okay, it's a good question. I don't want to give you my own definition. So I Googled it. Google has all the answers, right? And this is what it reads. A stationary point of a function f of x is a point where the derivative of f of x is equal to 0. These points are called stationary because at these points, the function is neither increasing nor decreasing. According to this definition, if you're willing to accept it, you may want to challenge it. But according to this definition, a stationary point is a point where a function is neither increasing or decreasing. I thought we couldn't increase or decrease at points. Well, based on the definition of a stationary point, it's a point where the function is not increasing or decreasing. That seems to be implied that there are points where a function is increasing or decreasing. Okay, ladies and gentlemen of the jury, I present the following information. Okay, if you don't accept that. Here's a type of problem you're very familiar with. And so say I have some position function. Let's say s of t. Well, actually, let me state a function that's like rectilinear particle movement. Let's say a function x of t is say x squared minus x of t. Pardon me, rough day. All right, so let's say x of t is t squared minus 6t plus 19. Let's say that's some function that describes the movement of a particle. And this particle only moves on the x-axis, so it either moves left or right. And so a typical calculus question would be something to the fact of, is the particle moving left or right at time, say, t equals 5? So is the particle moving left or right at this time, say, t equals 5? Well, the way you would solve that question is you would take the derivative of this function, which is known as the velocity function, if you take the derivative of the position function, and that velocity function will be 2t minus 6. And then to determine its movement, whether left or right, you would plug in that point. So I think I said 5. So v of 5 would be 2 times 5 minus 6, and that would be 4. And the conclusion would be, since the velocity is positive at that point. Now, I'm not saying positive over some interval. Since the velocity is positive at that point, the conclusion would be that the particle is moving to the right at the point, at the time that t equals 5. That would be the conclusion. So you're telling me I can determine whether a particle is moving to the left or to the right at a particular point, not on an interval, not comparing this location to that location, but at a particular point. You're telling me I can determine under popular prevailing conceptions whether a particle is moving to the left or the right at a point, but I can't tell whether a function is increasing or decreasing at a point. And we say that a derivative is an instantaneous rate of change, where it's able to tell us all these things at a particular instant. But it can't tell me if a function is increasing or decreasing at a particular instant. That seems to go against all the other type of problems that we do in calculus. Another type of problem, say the rate at which people are entering a building is some particular function. So the rate at which people are entering the building is some function E of t. So E of t is the rate at which people are entering the building. And I want to know if the rate of people entering the building is increasing or decreasing at some time t. Again, what I would do is I would take the derivative of this function, plug in that value for t, and if that value was positive, I would say the rate was increasing at that particular time. And if the value was negative, I would say that rate was decreasing at that particular time. So in all these different aspects, these different problem scenarios, we are able to deduce using the first derivative if something is doing something or the other at a particular instant, because a derivative is in fact an instantaneous rate of change. But we can do it for all these things. So for the movement of a particle, for whether acceleration is increasing or decreasing or constant, we can do that at points, not at intervals. We're not talking about an average rate of change. Whether the function is left or right, acceleration increasing, decreasing, whether a rate is increasing or decreasing. We can do all that stuff at a particular instant. But we can't determine if a function is increasing or decreasing at a particular instant. See if that makes sense to you. So to me, it's one or the other. If I cannot determine if a function is increasing or decreasing at a particular instant, then I cannot determine if a particle is moving left or right at a particular instant. Then I can't determine if acceleration is increasing or decreasing at a particular instant. Because the same logic would follow for the particle, if you will. To tell if a particle is moving to the left, well, I have to compare it with 2 points at 2 particular times. I can only see if it's moving to the left, see its position from one place to the next place. That's the only way I can tell the logic goes. I can't tell if it's moving to the left or right at a particular point. But the deal is, if I say a particle is moving to the left at time t equals 3, that means it's in the process of moving right through that point. It moves to the right through that point, right? Now, when a particle is at rest, when its velocity is at 0, and when its velocity at 0, that will be a stationary point for the position function. When a particle is at rest, we would say it's not moving to the left nor to the right at that particular time. We would say that with quite confidence. And that is quite similar, right, to stating that a function is not increasing at a particular point, or that a function is increasing at a particular point, or a function is decreasing at a particular point. So the notion that functions can only increase and decrease on an interval based off of first derivative analysis, I claim is false. And I claim because of that, the notion that the function f of x equals x cubed is strictly increasing from negative infinity to infinity is also false. The function is not increasing at x equals 0. Ladies and gentlemen of the jury, I presented my evidence, and now the ruling is in your hands. We'll see you next time.